Welcome back, reinforcement learning. This session I explain the intrinsic curiosity module. Okay, intrinsic curiosity module we discussed on Super Mario Bros. Game. In last session, we set up the DQ and policy function for the Super Mario game. After set up the DQ and policy function, now we are set up the intrinsic curiosity module for Super Mario games. So, intrinsic curiosity module is a reinforcement learning mechanism to design to enhance the exploration in environments with sparse extrinsic rewards. We apply the intrinsic curiosity module for to solve the infrequent rewards environment games. So, it provides the intrinsic reward signal based on the prediction error of the an agent forward dynamic model. So, this model encourages the agent to explore the states that are challenged to predict, thereby fostering the curiosity driven learning. The components of intrinsic curiosity module, we have the components encoder and forward model and reverse model. Encoder model, it encodes the states. A conventional neural network that encodes the raw input states into a low dimensional latent space. So, a conventional convolutional neural network that encodes the raw input states into a low dimensional latent space, that is the encoder operation. It converts the from high dimensional into low dimensionals. So, the architecture has the 4 convolutional layers with exponential linear unit activation function ELU in each convolutional layer, and output is flattened 288 dimensional vector. So, this is the encoder. This converts the high dimensional frames into video frames into low dimensional frames, grayscale images, that is the encoder states. Next one is the forward model, is the one of the component in ICM. In forward model, it predicts the next state. Predict the next state, the pi of st plus 1. We are implementing pi indicates encoded states given the current encoded state and the action state. The forward model predicts the next encoded state based on the current encoded state and applying action on that state. So, this architecture contains the two fully connected layers, and input is encoder state and action. Encoder state connected with one hot encoder and action. Next output is, we got the next state, 2-dimensional tensor. We are using rectified linear unit activation functions in these 2 layers. So, this forward model implements the 2 fully connected layers. These layers are using ReLU activation functions. So, it predicts the next encoded state of the encoded current state and action on that state. Next component is inverse model. This inverse model predicts the action taken at AT based on the 2 consecutive encoded states, pi of st and next state, pi of st plus 1. So, it predicts the action, which action leads the one encoded state into another encoded state. So, in this architecture we are implemented with the 2 fully connected layers. Input is concatenated encoded state, that is 576 dimensional in this example. Output is probability distribution over the actions. It predicts the actions. So, the 12 dimensional with the softmax applied. In Super Mario games we have the 12 actions, so output is 12 dimensional 12. So, we are applying the softmax for probability of the probability distribution of the actions. That is why we are using in this layer the softmax activation function. So, uses ReLU activation function in first layer. So, this is the inverse model. Okay, these 3 are the components in ICM model. The first one is the encoder, the second one is forward model to predict the next encoded state, and inverse model predicts the action, which action leads the one encoded state into another encoded state. The next one is working mechanism. The working mechanism of the Super Mario games implementation, the first one is input output overview. So, what is the input, what is the output? So, the first one is input to the any algorithm is, any model is the state, the current state B into 3 into 42 by 42, B is the batch size, 3 is the RGB colors, and height and width, the 42 into 42 is the space representation, and action, this is the 12, and next state ST plus 1. Okay, these are the inputs. Input is the state representation, current state with the batch size, number of samples, and 3 into 42 into 42. 43 is the channels, 42 by 42 indicate the spatial representation, and action and next state. What is the output of this one is the forward model prediction error. Output is error, the prediction error. Prediction error is used in intrinsic reward. The inverse model error, it is used to train the encoder and inverse model. We got the forward error, forward model prediction error, and inverse model error. So these errors are, based on these errors, we train the models. Training signal. So we have the two errors, forward model prediction error, inverse model error. Based on these errors, we train the model. Forward model error measures the difference between the predicted and actual next encoded states. It is used to what the next forward error. Forward model is predict the next state. So it predicts the difference between the current predicted state and actual next state. So used in this intrinsic reward. And inverse model is it predict the actions. So measure the accuracy of predicted actions based on the encoded states. Train the encoder to retain the relevant feature for action predictions. So we train the models with the training forward model error and inverse model errors. So working mechanisms is we have the loss function, the combined loss function for the ICM and DQN this is the formula for combine the both ICM loss function ICM and DQN, and we scaling the parameters for the DQN loss, and B is the balances for the forward and inverse model losses. And intrinsic reward, the calculated as the forward model prediction error and combined with the extrinsic reward. If available, we have the extrinsic rewards to form the total rewards. So reward is rewards of intrinsic plus rewards of extrinsic. So we are using the loss function and the intrinsic rewards to optimize the results. In implementation point of view, this is the encoder model Python code. We have the 4 convolutional layers, and this is the forward model. In forward model, we are using the 2 linear layers, and inverse model, we have the 2 linear models. So limitations and further research for this is the curiosity model. It is the sensitivity to the hyperparameters such as the learning rate, batch size, and scaling coefficients. So in this point of it is a very sensitive to the hyperparameters. Adversarial dynamic between the DQN and the forward model can make the convergence noisy in DQN point of view and forward model. And the alternative intrinsic reward mechanisms like Bayesian inferences and empowerment strategies are gaining attraction as a complementary for the superior methods. So we have some more intrinsic reward mechanisms, Bayesian and empowerment strategies are gaining the traction for the some drawbacks of this intrinsic curiosity module. So the applications and performance, we are using the intrinsic curiosity models in Super Mario Bros games, which games have the infrequent space rewards, and we train the models with the prediction error based reward mechanisms, which games are used to train the models with the prediction errors. And this type of application we are using intrinsic curiosity module. Thank you.